Okay, first we have the statistics, and remember that I clarified you can only use each letter as much as it appears. That was the assumption there. So you could use an S up to 3 times. Otherwise, you're not going to be able to make a 10-letter rearrangement. So we have that. It's a multinomial probability, but we've used this formula before on words where we have 10 factorial would be the total amount of arrangements if each letter was different. And then since we have 3S's, we're going to have duplicates that we have to divide out, 3 T's and 2 I's. Now B, if we could reuse a letter as much as we want, then we only have 5 possible letters to choose from, ACIST, and we'd have 10 slots where order does matter. So putting an A in the first slot is different than putting an A in the second one. So we'd have 5 letters for the first slot, 5 for the second, 5 for the third, and be 5 times 5 times 5 repeated 10 times there, so 5 to the 10th. Mathy, so we're again dividing this up into cases. So 1-letter words, since there's no duplicates, this is a bit easier than the practice exam, which just be 5. We have 2 letters, 5 choices for the first, 4 for the second, and so on. Notice that both 4 and 5 are 5 factorial because this one is ends with times 2, and this one ends with times 2 times 1, which are the same thing. Okay, so if we roll 2 dice, assuming that both dice show a 3 or higher, so already with this given assumption, the 1s and 2s are out of the picture entirely. They're not even in our sample space. So our sample space is anything between 3 and 6 on one dice and anything between 3 and 6 on the other dice. And then we're interested when the sum will equal 8. So it would be right here, here, here. There would be 3 different cases out of 16 total, which is 3/16. Notice that there's not, although there is a 5-3 and a 3-5, there's not 2 4s. So we don't have a 4-4 and a 4-4 as separate. And you can see that when you draw out this sample space right here to see the 16 options. But it can be confusing if you try to reason other ways. Okay, we have the binomial theorem where our left term here is 3x and our right term is negative 2y squared. So when we're asking ourselves where we're at, how many of the lefts we're taking, it's pretty clear we're taking 10. It's the only way we'd get a power x to the 10th. And then of the right, just to check, notice that we have a squared power. So every time we take one of those, it adds 2 to the power of y. So to get y to the 14th, we would have to have 7 of these. So we have 10 of these and 7 of these. And that adds up to 17, as it always should. So notice that our k here, we can really use either 7 or 10, either the numbers of lefts or the numbers of right terms. Either one would be perfectly fine. So 17 choose 7 or 17 choose 10. And then since we're only looking at the coefficient here, this coefficient 3 is going to get raised to the 10th power. The coefficient of negative 2 here is getting raised to the 7th power. Okay, I would strongly recommend a Venn diagram on this. Some people tried to reason it out, which is fine as long as you make solid logical steps at every point, but it takes away the ability to visualize the big picture here. So we have the young, the male, and the married. And notice when I put a number into my Venn diagram, it only represents the number within that little chunk of that circle. So in other words, this 319 doesn't mean there are 319 married. It means there are 319 married that are not young and that are not male. In other words, old female married people. There's 319 in our sample. Okay, so we just use these numbers and we fill in everything except I think it's the 88. So as soon as we know It's easiest to start at the end. So we have 60 young married males. We put that 60 in the middle. If we wouldn't have that for some reason, so if they would not give us this number, we could always just put an X there and continue and then write out some equations. So if we knew there was 120 married males, married young people, and we knew that this was X, then this would be 120 minus X. So it is possible to use a variable to represent one of these areas that we don't know. And then keeping in mind that there could be people out here, and often there are. So what would the people out here represent? Well, they would be the old single females, because they're not part of any of these three groups. So people out here would be old female single ladies. Okay. That's horrible type there, but we have 30 types of pizza to choose from, and we're going to choose 3 of those 30. So this is one of our classic problems, like the wallet, the coins in the wallet that you did for the good problem. So 30 different categories of pizza, which means 29 walls, and then we have these 3 pizzas that we can put into any of these 30 categories. So 29 dividers, 3 pizzas gives us 32 possible spots, and then we're choosing either 3 pizzas or 29 places to put the dividers. So either of these would give you a correct answer. Notice it would not be 30 times 30 times 30. The reason being, if you're saying that, that would make pepperoni sausage different than sausage pepperoni sausage, or pepperoni sausage. So because order doesn't matter to us, it's not like the first pizza is different than the second or the third. We have this situation right here where we just put these pizzas somewhere into these categories, but it doesn't matter. For example, if we had 3 in this 30th type, it wouldn't matter which order those 3 are in. Okay, we have another one of these card problems. 7 cards, we need to get exactly 3 kings. Well, there's only 4 kings to choose from, and we're going to choose 3 of them. So first we choose our 3 kings. Now we need to choose 4 more cards. And instead of having 49 to choose from, because technically there are 49 left, we only chose 3 of the kings. But since we need exactly 3 kings, then it's going to be 48 non-kings left, and we want 4 of them. And of course then, out of the 52, we're choosing 7, would be the total number of hands we could get. Same logic, 2 of the 4 aces, then we need 5 more cards out of the remaining 48. And notice, now we're not worried about getting a king here. It would be okay if we got a king at this point. And here, we need both exactly 3 kings and 2 aces, so we choose 3 of the 4 kings, 2 out of the 4 aces. We have 44 remaining cards that are permissible, remember, because we can't get a king or an ace. We don't want a king or an ace. So 44 left to choose from, we want to choose 2 of them. And then finally, we want to know to get exactly 3 kings or exactly 2 aces. Well, that, according to our probability law, is probability of getting 1 plus probability of getting other minus that intersection, which is basically the answer for A plus the answer for B minus the answer for C. Okay, finally we have a set of numbers here. 6 numbers. How many 4-digit numbers can be made that are odd? So we know that that last number can either be a 1, 3, 5, or 9. We have 4 choices if we want that to be odd. So go ahead and choose that. And then we could go backwards here, 5 choices for this one, 4, and then 3, or 5, 4, 3. There's really, doesn't matter where we choose our second one, our third one, and our fourth one for part A, as long as we chose that first one right here, and notice then that there would only be, no matter what we chose here, there would be exactly 5 leftovers for the next step. Okay, consisting only of only odd digits. Well, this one's actually a bit easier because we only have 4 odd digits available, and so if we have to consist of 4 odd digits, we have 4 choices for the first one, 3 for the second, 2, and then 1. And again, keep in mind that this is still under the assumption we can use each digit no more than once. Otherwise, we could have 4 to the power of 4 to the 4th power. Are even and less than 3,000. Okay, so we're going to have 2 constraints. One is it has to be even. So it has to end in either a 2 or an 8. But it also has to be less than 3,000. So it has to start with a 1 or a 2. So if you do either one, let's say we did step 1, choose your first number, and then we'd have 2 choices there. And then step 2, choose your last number. Well, we don't know how many we have available because we don't know if we grabbed an odd number at first or if we grabbed an even number at first. And so one way I think is easier to do this one is split it up into 2 cases. So either you get a 1 or you get a 2. If you get a 1, then there will be 2 choices remaining for the last one to be even because you didn't eat up one of the evens yet. And then after you do those 2, it doesn't matter if you go 4-3 or 4-3 because either of these can use any of the remaining ones after you choose the first number to be less than 3,000 and the last number to be even. Okay, so this gives us 24 ways up here. And right here, we choose a 2, our second step. That only leaves us one option here. We have to choose the 8 right here. But after we've chosen those 2, the 2 here and the 8 here, then we have 4 choices for this one and 3 for this, or 4 for this and 3 for this. It doesn't matter which order. Now, this is a little bit tricky here. Notice that we have 4 times 3, which gives us 12. This 2 is not getting multiplied. This is just the name of the case. This is the case where 1 is the leading digit, the case where 2 is the leading digit. So it's not actually getting multiplied in there. Okay, and have the digits in increasing order. Okay, why do I say 6 choose 4 here? Well, out of these 6 numbers, all we need to do is choose 4 of them. And since we can't use a digit more than once, there's only going to be one way to write those 4 numbers. If we chose 1, 3, 9, and 8, it has to be 1, 3, 8, 9. That's the only possible way. So that's going to cover all the possible combinations of 4. And each combination of 4 will have exactly one way which it can be written in increasing order. So that gives us 15 different possibilities. And for the extra credit, this is one where we just have, because we can reuse them, we have 6 different categories, which is 5 dividers, 4 different digits, each gets a ball, so we have basically 9 places. We're going to choose 4, or we could have 9 choose 5, same thing. And why do we say this, that it must be a non-decreasing? Well, as soon as we get our specific combination there, so there's 126 of these, there's only going to be one way to write them. For example, if we had 2 3s and an 8, it would have to be 3, 3, 8. If we had a 2, a 1, and a 9, it would have to be 1, 2, 9. There's only going to be exactly one way to write each of those. So 126 total ways. Okay, as always, let me know if you have specific questions.